All right, welcome to The Explainer. And listen, this isn't going to be some dry, boring textbook lesson. No, today we're actually going to unlock the invisible rules that power, well, everything. I'm talking about the phone in your hand, the lights over your head, all of it. So let's dive right in.
Seriously, just think about it for a second. Every single day, right? You're using dozens of different gadgets. But have you ever stopped to wonder what is actually going on inside all those wires and circuits? What are the basic, fundamental laws of physics that make it all, work? Well, that's exactly what we're about to find out.
Okay, first up, the spark. We're talking charge and current. You see, it all has to start somewhere. And for electricity, it all begins with the most basic building block you can imagine. Something we kind of take for granted, electric charge. This is literally the spark that gets everything else going.
Remember when you were a kid, you'd rub a plastic ruler on your sweater, and then, boom, it would magically stick to your hair or pick up tiny little bits of paper. Well, that's a real thing called electrification. What you're doing is literally just moving charge from one thing to another using friction. It's such a simple act, but it's a perfect, real-world example of this invisible force we're going to be talking about.
Okay, so if we have this stuff called charge, scientists and engineers are going to need a way to measure it, right? So they came up with a standard unit. It's called the coulomb, and we just write it as a capital C. You can think of it as our official measuring stick for how much electric charge there is.
So, what on earth is a coulomb in real life? Well, check this out. Grab your phone, look at your laptop battery. You've probably seen that AH unit, right? That stands for amp hour. And get this, one single amp hour is the same as 3,600 coulombs of charge. So that number is telling you the total amount of charge your battery can spit out in 1 hour. All of a sudden, it's not just some random science term, is it?
All right, next section, the gatekeepers, resistance and conductance. So now we've got charge, and it's moving, it's flowing. But what if it just flowed wild and free? Well, our gadgets would just fry. So obviously, we need a way to control that flow. It's time to meet the gatekeepers.
This opposition to the flow of current, that's what we call resistance. And it comes down to three and only three simple things. The easiest way to think about it is like a water pipe. The longer the pipe, the more friction, right? So a longer wire equals more resistance. Make sense? A thicker pipe lets more water gush through, so a thicker wire means less resistance. And obviously what the pipe's made of matters. Copper is like a slick, wide-open pipe. And here's the real kicker. It doesn't matter if the wire is all twisty and wound up. That shape is totally irrelevant. Only these three things count.
And for every force that pushes back, there's one that helps things along. So if resistance is all about how much something fights the flow, its exact opposite, which we call conductance, is all about how easily it lets that current pass through. They're literally just two sides of the same coin. Mathematically, one is just one divided by the other. It's just two different ways of describing the very same property of a material.
Okay, now this is where things get really interesting, because how you wire things up is absolutely critical. If you connect components in what's called series, one after the other, it's like a single-lane road. The resistance just keeps adding up. But if you connect them in parallel, you're creating multiple paths. It's like opening up more lanes on the freeway. And the amazing thing is, the total resistance actually drops, which lets way more current flow through. This idea is just fundamental to how all circuits are designed.
Okay, on to our third part, the invisible force, magnetism. So let's recap. We have charge, we have that charge flowing, and we have ways to control it. But there is another massive piece to this puzzle, a kind of hidden partner to electricity that honestly makes most of our modern world possible, and that is magnetism.
And this right here, this is one of the most fundamental rules in all of physics. It's so simple, but so powerful. Anytime you have an electric current, anytime charge is on the move, it always creates a magnetic field. Always. They're not two separate things. They are deeply, deeply connected. Two faces of the same fundamental force.
So that's cool, but how do we actually use it? Well, the easiest way is something called a solenoid. And it's super simple. You just take a wire and wrap it into a tight coil. That's it. When you do that, all the little magnetic fields from each individual loop of wire, they all add up. They get concentrated into this one super strong, really useful magnetic field right in the middle. I'm not kidding, this simple idea is the secret behind pretty much every electromagnet, electric motor, and power generator out there.
And yeah, of course, we can calculate the oomph behind this magnetic field. This number you see, 300 AT, stands for magnetomotive force. It's a fancy term, but just think of it like magnetic voltage.
It's the pressure that's creating that magnetic field. And the math is just beautiful. It's simply the current you're putting in this case half an amp, times the number of times you wrap the wire, 600 turns. That's it. It's this incredibly direct, powerful connection.
Okay, section 4, the law of opposition. Now, I have to admit, this next concept is one of my all-time favorites in physics. It's a little weird, a little counterintuitive. It's almost like the universe itself is just kind of stubborn. It's called Lenz's law.
Just read this. Let it sink in. It's a really wild idea. You push current into a coil, the coil pushes back against you. You try to stop the current, and the coil tries to keep it flowing. It's like electrical inertia, like the universe just doesn't like change. It's amazing.
So here's what's happening. This pushback from the coil, it isn't just some abstract idea. It creates a real, actual, measurable voltage that fights whatever you're trying to do. We call this property inductance. And the crazier part is, the faster you try to change the current, like really ramp it up or down quickly, the harder that coil pushes back, creating an even bigger voltage. It's this dynamic, reactive force that is just so essential for how so many electronics work.
All right, final section, powering our modern world. Let's pull everything we've talked about together. We've got charge, resistance, magnetism, and this weird pushback called inductance. Now we get to see how all these pieces fit together to run our entire planet through what we call alternating current, or AC power systems.
Okay, so remember how we said a moving current makes a magnetic field? Well, the genius Michael Faraday figured out that the street runs both ways. If you take a magnet and move it, if you change the magnetic field near a wire, you will force an electric current to flow in that wire. And this is everything. This is the discovery that literally powers our entire civilization. Every single power plant works on this one principle. Spin a huge magnet inside a huge coil of wire to make the electricity that you're using right now.
Now, because the power coming into our homes is constantly changing direction, that's what alternating current means, it's always flipping back and forth, resisting it gets a little more complicated. It's not just that simple resistance we talked about. No, the total opposition in an AC circuit has a different name, impedance. And it's made of two parts. The normal resistance of the wire plus that reactive, stubborn pushback from inductance that's constantly fighting against the current as it tries to change.
And this leads to a really important and kind of weird final point. In these AC systems, not all the power that you draw is actually doing any work. See, the power company has to send you the total amount, which we call apparent power. But part of that power, called reactive power, is basically ghost power. It's just borrowed for a split second to build up all those magnetic fields and things like motors, and then it gets sent right back. It sloshes around in the grid but doesn't actually do anything useful. The only power that really matters to you, the stuff that actually makes your toast or lights up your screen, is what we call real power. That's the stuff measured in watts. And so we've come full circle. We went from a little spark of static electricity on a toy ruler all the way to this incredibly complex dance of energy that powers our entire global grid. These laws, these ideas, they're the bedrock of the modern world. And the wild part is, most of them were figured out more than 100 years ago, which really makes you stop and think, doesn't it? What's the next great principle we haven't even dreamed of yet? What's the next thing we're going to uncover? Thanks for joining me.